Hello, welcome to part 2 of this video about Woodstock's first trip to the sea at Southampton Water. He's back in his garage on our amazing stand. I haven't yet got used to the fact that he can rock so easily on this. Anyway, this video is going to be short and technical about the data that we got on the SD card from the autopilot during his sea trip and what use we can make of it. So let's get on. You'll recall that we sailed the boat in a circle of about 160 meters diameter like this in order to test at all angles to the wind. And one of the interesting things about this is the scalloped nature of these steps from P7 to P8, P9. If we go back to there, where it's starting out, see that the boat is pointing at P8, which is where it's trying to go to. The wind is blowing across the boat from behind, as shown by the magenta arrow, and the actual course of the boat is slightly to starboard of the direction it's pointing. In other words, the boat is moving in a kind of crabwise fashion through the sea. This is perfectly normal for a sailing boat, and it's called leeway. The tendency of the boat to move partly in the direction that the wind is blowing on it. So that's what causes this curve. You may wonder why, if the boat is constantly pointing at P8 and it's actually travelling to starboard of that, how does it ever actually get to P8? Well, the reason for that is that as it moves, the autopilot is every 10 seconds or so correcting the desired course. And as it gets closer to P8, those corrections become bigger and bigger, as you can see there. So eventually it actually gets to P8. We can see this on the telemetry, where this dark red line is the desired course, which starts out at -41 degrees and ends up just before we get to P8 at -51, so all of 10 degrees further to port. This blue line is the course over ground, the actual course of the boat, which we see is -27 degrees here, whereas we're asking it to go at -41. So the leeway is carrying it all of 15 degrees further to starboard than intended, despite, as shown by the green line, which is the actual heading of the boat, that despite the heading being kept as desired by the navigator. The normal way of dealing with this problem is that if you start out sailing supposedly to P8 and you notice that actually you're sailing at a more starboard angle, then you should adjust your heading somewhat to port of P8 so that you actually sail directly at P8. That's called cross-track error correction, and it's a logic that we haven't yet put into the boat, but we will do. You'll recall that we fitted a wind vane and a cup anemometer to the top of the mast, and we're recording that data once every second to the SD card. This wind vane is fine for test purposes, but it's not really waterproof. This joint up here isn't waterproof, this joint here isn't waterproof, and there are holes in the bottom. So if it was in the sea and was regularly being dunked under waves, it would soon stop working. So we need a better way of measuring wind direction for the real boat. One of the ideas of deliberately sailing the boat in a circle like this was to see if we could deduce the wind direction from other information that we are collecting. One of the things that we collect, for example, is roll angle, which you can see here as the boat moves. So we wondered if we could deduce the wind direction from the roll angle. Here is a histogram of the wind direction whilst we were sailing round that circle. It averages 159 degrees, but it varied between 110 and 190 degrees, as shown by this histogram here. And this is an alternative graphical presentation where you can see that the average, on average, the wind is blowing from 159, but it covers this whole sector here. And the wind speed whilst we were going around the circle averaged 5 mph, but varied between 3 and 7. It took us about 55 minutes to sail around the circle from P1 to P15, and during that time we managed to take 6,500 readings of the wind direction. What this plot shows is the average roll angle of the boat for each possible angle of the wind to the boat. So, for example, if we take this point here, it shows that when the boat was sailing at an angle of 135 degrees to the wind, its average roll angle was minus 10 degrees. Hope you can see that dim minus 10 degrees on this radial scale. And similarly, when the boat was sailing at 225 degrees to the wind, the average roll angle was just short of plus 5 degrees, i.e. 5 degrees to starboard. This black line here is the line of zero roll, 0 on this radial scale. So the way we deduce wind angle from this plot is to go round the red line and see when it crosses the black circle, the circle of 0 roll. And it crosses this circle at 176.5 degrees. So if we go slightly to port of that angle, the boat is rolling to port, and if we go slightly to starboard of that angle, the boat is rolling to starboard. This is the point where the boat is facing directly into the wind at 176.5 degrees. If we follow the line round again, we get to the opposite point where the boat is running directly downwind, which is at 320 degrees. So that gives us another reading for wind direction of 320 minus 180 equals 140. And then if we average those two readings, we get 158.6 degrees as the average wind direction. If you can remember, we go back to the actual measurements we made, we decided that the average wind direction was 159 degrees from the wind vane. So this is a pretty good agreement between these two methods of measuring the wind, the real one and the roll angle. So we're quite pleased with that. But what I would say is that the waves in Southampton Water are rather feeble, and we need to test this again in a much more heavier sea where more rolling is induced by wave motion. But so far so good. Another reason for sailing in a circle is to try and derive the polar diagram for the boat. And this is the result we get on the red line, which shows the GPS speed over ground for each angle to the wind that the boat is sailing at. As one expects, we get a very low speed when it's pointing directly at the wind, and if you established 0.6 mph as a target speed, then you could say that you've got to sail at more than 40 degrees to the wind on the starboard side, or more than 75 degrees to wind on the port side. So there's an asymmetry there in the data. hopefully not in the boat itself. All the polar diagrams I've so far devised have some kind of asymmetry like this, and I'm not quite sure why that is. If anybody has any idea, welcome to add something to the comments and let me know. On Bray Lake we had the impression that Woodstock tends to roll far more than it pitches, whereas in the sea at Southampton Water we got the impression it was pitching much more than it was rolling. Well, we've now got the statistics for that, so I'll show them to you. On the right we have the statistics on Bray Lake in quite high winds, and on the left the statistics in Southampton Water in slower winds. Clearly there was more roll on Bray Lake than there was on Southampton Water. And equally there's slightly more pitching on Southampton Water than there was on Bray Lake, but it isn't as pronounced as I thought it would be. I suppose that pitching at plus or minus 5 degrees is happening about 60% more often than it was happening on Bray Lake, but not an enormous difference. Another concern that I have with the boat on a constant heading, the rudder seems to be very busy. It's constantly twitching backwards and forwards, and I'm not quite sure why this is. It could be that it needs to do this to maintain a constant heading, or it could be that the tilt compensation of the compass is not as good as it should be, and that all this pitching and rolling is causing fake compass movements. This is something we've got to investigate, because it's going to wear out the rudder servo and use up an awful lot of power, which we can't really afford if it goes on like that all the time in the sea. This boat's quite heavy, and I'm glad it is Dick who volunteers to do this work. My back isn't that good.